Welcome back. In this blog, I will give an answer to the question, how do we make a silicon wafer? How can we make the silicon material pure? The learning objectives are to get familiar with the appearance of mono and multicrystalline silicon, the various production processes from raw material to high purity grade silicon, and the production techniques for silicon wafers. For a long time, crystalline silicon PV technology has used two types of silicon wafers, the monocrystalline and the multicrystalline silicon. These terms already give away the difference between the two materials. Monocrystalline silicon is a single crystal having the same lattice orientation throughout the entire wafer. For multicrystalline silicon, grains of a single crystalline material with different lattice orientations are side by side, having dimensions in the order of millimeters to nearly a centimeter. The different appearance is evident from the pictures in this slide. At the grain boundaries of multicrystalline silicon, we find lattice mismatches. As a result, many defects or impurities reside at the grain boundaries. Consequently, the lifetime of the charge carriers in multicrystalline silicon is shorter than for monocrystalline silicon due to the Shockley-Reed-Hall recombination. Consequently, solar cells made out of multicrystalline silicon wafers have a lower conversion efficiency in reference to monocrystalline wafer-based solar cells. For a long time, the much cheaper production process of the multicrystalline silicon wafers allowed the production of silicon solar cells with lower performance in reference to the expensive monocrystalline. However, due to upscaling of the monocrystalline silicon production, this wafer type has become much cheaper as well. The last year, multicrystalline silicon production phased out quickly and monocrystalline silicon solar cells production have taken over the market. Therefore, in this video lecture, I will only focus on the production of monocrystalline silicon wafers. Silicon is the second most abundant material on Earth, right behind oxygen, as the crust of Earth consists for 90% of silicon-based compounds. Silicon dioxide or silica is found in forms sand, sandstone and quartzite. Now, wouldn't it be great if we could take a few buckets of sand from the beach and process that into a solar module? In principle, this is possible, but high-efficiency solar cells require a high level of purity of the silicon base material. In this video lecture, I will discuss the processing steps from the raw material quartzite to a wafer. Quartzite is a rock of almost pure silicon dioxide. The oxygen should be removed from this compound in order to obtain so-called metallurgical silicon, here shown in powder form. This is the lowest quality processed silicon. In the next animation, the process of making metallurgical silicon out of quartzite is shown. During the production, the silicon is purified by removing the oxide. This happens in a submerged electro arc furnace. The quartzite is moved into the furnace where it's melted. Using an electrode, the quartzite is heated up to a temperature around 1900 degrees Celsius. The molten quartzite is mixed with carbon. The carbon source is a mixture of coal, cokes and wood chips. The carbon reacts with the silicon oxide. I won't discuss in details of the reaction, which is rather complex, but the result is that the oxygen is leaving the furnace as carbon monoxide. The molten silicon that is formed is drawn to the furnace and solidified. The purity of the metallurgical silicon is around 98 up to 99%. 70% of the worldwide produced metallurgical silicon is used in the aluminium casting industry to make aluminium silicon alloy parts, which are used in the automotive engine blocks. The other 30% is being used to make a variety of chemical products like silicones. Only around 1% of the metallurgical silicon is used to make electronic grade silicon. The silicon material with the next level of purity is called polysilicon. In the next animation, you see how out of metallurgical silicon, rods of polysilicon are produced using the Siemens process. The source material is powder of metallurgical silicon. The metallurgical silicon is then exposed in a reactor with hydrogen chloride at elevated temperatures in presence of a catalyst. The silicon reacts with the hydrogen chloride and starts to form trichlorosilane. This is a molecule that contains one silicon atom, 3 chlorine atoms and 1 hydrogen atom. The trichlorosilane gas is cooled and liquefied. Impurities with higher or lower boiling points are then removed using distillation. The purified trichlorosilane is evaporized again in a different reactor and mixed with hydrogen gas. Trichlorosilane reacts with the hot rods, which are at a high temperature of 850 up to 1050 degrees Celsius. The silicon atoms are deposited on the rod, whereas the chlorine and the hydrogen atoms are desorbed from the surface of the rod back into the gas phase. As a result, a pure silicon material is grown, and this deposition method is called chemical vapor deposition. As the exhaust gas still contains chlorosilanes and hydrogen, these gases are recycled and used again. Chlorosilane is liquefied and distilled and reused. The hydrogen goes through a cleanup process and is recycled back into the reactor. Another technique to obtain polysilicon is by using a fluidized bed reactor. Here the metallurgical silicon is fed into the reactor as silane gas, which has the chemical formula SeH4, while small crystalline silicon seed particles are fed from above. This forms a fluidized bed, and the silane will decompose onto the crystalline silicon particles that will start to grow in size, and which will eventually fall to the bottom of the reactor when they are large enough. Overall, this process consumes about 90% less energy than is required for the Siemens process, and it can run continuously. However, the purity of the obtained polysilicon is slightly lower than the Siemens process. Using either the Siemens process or the fluidized bed reactor, the polycrystalline silicon can have a purity as high as 99.9999%. Or in other words, 1 out of a million atoms is not a silicon atom. In the next step, we will discuss 2 different methods to produce wafers in which the raw polysilicon materials will be processed in large cylindrical monocrystalline ingots, which will then be sliced into wafers. But first we consider 2 methods to make monocrystalline silicon ingots. Ingots are large blocks of crystalline silicon. The monocrystalline ingots are solids that consist out of one big crystal. In the next animation, you will be introduced to the Czochralski processing method. Let's start with the Czochralski method, as developed by the Polish scientist Jan Czochralski in 1918. It's a method to grow single crystalline silicon. In this method, highly purified silicon is melted in a crucible at typical temperatures of 1500 degrees Celsius. Intentionally, boron or phosphorus can be added to make p-doped or n-doped silicon, respectively. A seed crystal that is mounted on a rotating staff is dipped into the molten silicon. The orientation of the seed crystal is well defined. It's either a 100 or a 111 orientation. The melt solidifies at the seed crystals and adopts the orientation of the crystal. The crystal is rotating and pulled upwards, allowing the formation of a large single crystal cylindrical column from the melt. This big single crystalline silicon block is called an ingot. In this process, the temperature gradients, rate of pooling up and speed of rotations are precisely controlled. This process is further developed and through years of advances, and nowadays crystal ingots of diameters of 200 to 300 millimeters with lengths of 2 meters can be processed. To prevent the incorporation of impurities, this process takes place in an inert atmosphere, like argon gas. The crucible is made from quartz, which partly dissolves in the melt as well. Consequently, Cherkassky monocrystalline silicon has a relatively high oxygen level. The second method to make monocrystalline silicon is the so-called float zone process. This is a process which results in monocrystalline silicon ingots with extreme low densities of impurities like oxygen and carbon. The process is shown in the next animation. The source material is a polycrystalline rod as processed in the earlier mentioned Siemens process. The end of the rod is heated up and melted using a radiofrequent heating coil. The melted part is put in contact with seed crystals. Here it solidifies again and adopts the orientation of the seed crystal. Again, both 100 and 111 orientations are being used. As the molten zone is moved along the polysilicon rod, the single crystal ingot is growing as well. Many impurities remain in and move along with the molten zone. During the process nowadays, intentionally nitrogen is added, which improves the control on the micro defects and improves the mechanical strength of the wafers. The advantage of the float zone technique is that the molten silicon is not in contact with other materials like quartz as in the Cherkassky method. In the float zone process, the molten silicon is only in contact with the inert gas like argon. The silicon can be doped by adding doping gases like diborane and phosphine to the inert gas to get p-doped and n-doped silicon respectively. The diameter of float zone ingot is generally not larger than 150 millimeters, as the size is limited by the surface tensions during the growth. Now we know how to produce monocrystalline ingots. How do we make the wafers out of them? The answer is sewing, as you can see in the next animation. A disadvantage of the sewing step is that we waste a significant fraction of the silicon as kerf loss. The kerf loss is usually determined by the thickness of the wire or saw used for sewing and is in order of 100 microns of silicon. This is a large fraction of the ingot if you consider that typical crystalline silicon wafers used in solar cells nowadays are in the order of 140 up to 200 microns. Sewing will logically damage the surface of the wafers. So this processing step is followed by a polishing step. Summarized, we have discussed how out of quartzite we first make metallurgical silicon and then polysilicon. Monocrystalline silicon ingots are made using either the Cherkassky or the float zone process. Wafers are being made by sewing these ingots. Now we know how we make the wafers. Let's make solar cells out of them. We will discuss design rules in the next video, so see you in the next video.